Seeing that screen?
We do.
All right, perfect. All right. So thank you for inviting me to speak tonight with your group. As I kind of go through this work that I'll be talking about tonight, feel free to ask questions along the way, because there's some points that if you don't understand something, that you're not going to understand the next step in the process possibly. So I don't want you to have any confusion along the way. Hopefully that won't be a problem, but feel free to ask questions. So I'll be talking about brining as a stormwater best management practice. And this is a study that I did while I was at St. Louis University working on my PhD. Oh, sounds like there's something.
I'm going to stop doing that. I think that's me muting people, so I'm going to stop doing that.
Okay. All right, yeah, so this is research I did when I was at St. Louis University. It was funded by an EPA Urban Waters grant, which basically, as I mentioned, my PhD is in biology, and there's really, the work itself really doesn't have any direct biology in it, but I was able to get the grant from EPA, which funded the equipment that I was able to use then for the rest of my PhD, which was biology. So, just an example of using funds from one grant to help make other things happen too. So, and just wanted to have also mention quickly that I'm currently working at the National Great Rivers Research and Education Center, which is located in Alton. And so there I'm the director of the Illinois RiverWatch program. So if you're interested in doing water monitoring, there's a stream team in Missouri, and we've got RiverWatch in Illinois, so you can do water monitoring anywhere you want these days. All right. So I want to give you a little bit of background about road salt. I think most of you probably have lived in St. Louis long enough that you've seen salt on the roads. But the use of salt to improve the safety of travel with winter snow and ice storms is actually a relatively recent phenomenon, which first gained traction in the 1940s. So before that, we didn't use road salt. We just either drove on the snow and ice or stayed home. But since the 40s, the practice of using road salt, which is NaCl, the exact same salt that you use at your table, just a slightly less purified form. The use of that sodium chloride or road salt has spread into most parts of the world where snow falls. And so, as I mentioned, this road salt is mostly sodium chloride, but there is also other chloride salts used like calcium chloride and potassium chloride. But I'll be talking about salt and chloride kind of interchangeably throughout this talk. So just know that those are both pretty much the same thing when I'm talking. So the use of salt in the United States currently is more than 20 million tons of salt per winter in the United States. And the purchase price of that salt, the cities, when they buy it in bulk, is about $50 per ton. And so that comes out to about a $1 billion annual investment in safe transportation in the United States. Now, there's several consequences of using road salt. The first of these is that it is very corrosive to concrete and to metal. And so according to a study from 1992, 1 ton of salt, which again costs about $50, can do about $600 in damage to infrastructure. So this is just to roads and bridges. That doesn't include damage to cars. So we're doing about $12 billion in damage to roads and bridges in the United States every year. Okay, so we put that salt down on sidewalks, parking lots, roadways, and then it dissolves in the water, and then that salty runoff flows in some cases into vegetated areas like this grass lawn at SLU right next to the building that I was working in. And so that can do damage to grass, obviously, where you can see the grass has been basically burned from it. It's toxic also to street trees, to many plants that we would put in something like a rain garden where we intentionally direct our runoff. So that's another potential damaged by it. But then that salty runoff can either directly from the pavement or indirectly through a situation like this flow into a storm drain. And those storm drains flow into nearby streams. And so these are all freshwater streams, and the animals that live there have adapted to freshwater conditions. But every winter, the aquatic life in these streams is exposed to highly concentrated salt from runoff, and this potentially creates toxic conditions. But the salt doesn't just end up in our streams. It ends up in lakes, and it also can migrate into our groundwater. So both surface water and groundwater serve as our drinking water supplies. And so there's an increase in salt in these areas that in many places is raising concerns about drinking water safety. And that this is especially true for people with underlying health conditions like heart disease. Now in the St. Louis region, we currently don't have a problem with that because so much of our drinking water comes from Mississippi and Missouri River, where there's a lot of dilution, and so we don't really have that problem. But in places like New York, where they use a lot of salt and they get a lot of drinking water from their groundwater, there's entire parts of New York State where half of the people in that county cannot drink the water coming out of their taps because there's so much salt in the groundwater now. All right, so before I get into the work that I've been doing, I want to make sure that you have a kind of a good understanding of the basic numbers that are involved in salt in streams. So a natural stream will generally have less than 40 milligrams per liter of salt. So this is a pretty low number. This is before people settled in this area. There's very few streams that stay at this level and lower year round at this point. Now every state sets their own drinking water, or not, I'm sorry, their own water quality standards, including both for drinking water and for the support of aquatic life. And that aquatic life would include both fish and things like invertebrates, which is kind of more what I focus on. So the drinking water quality standard is about 250 milligrams per liter in Missouri. And that number is similar to the chronic aquatic life threshold, which basically means, chronic meaning exposure of about 4 days at 230 milligrams per liter can be dangerous to invertebrates and fish. And then the acute toxicity limit for aquatic life is 860 milligrams per liter. And so that's a bit higher, but that basically means if they're exposed to that level for an hour or thereabouts, then that can be toxic. And at that point, it's really toxic for some of the more sensitive organisms. It's not going to wipe out everything in a stream at that amount, but the things that happen to be sensitive to salt, they're going to be the first ones to go. And then just as a point of reference on the high end, seawater has about 20,000 milligrams of chloride per liter of water. So much higher than what we find for our standards here. All right, so the project that I'm sharing with you today began and were inspired by a group of trained volunteers with the Missouri Stream Team program who've been monitoring chloride in the winter at 63 sites in St. Louis County. They've taken about 3,000 chloride grab samples since 2012. And on this map, we see a summary of the locations and then the maximum chloride concentrations that have been found at sites across the St. Louis region. So just in case this map is different enough from what you normally see, this area is all the city of St. Louis, and then all of this is the county. This is the Missouri River and the Mississippi. Just to make sure everybody's got their frame of reference there. And so we have the most urbanization there near the city, and then as we move west, we have decreasing urbanization, and where we have urban development, we have roads, and where we have roads, we have salt. So the maximum concentrations that we're seeing in sites here, those are in red, and that means that the maximum concentration measured by volunteers was somewhere between 2,400 and 8,000. So that was actually the highest measurement that we got from the volunteers. But remember, this the dark blue here, this less than 230 milligrams per liter, that's the amount that's considered safe. Only safe areas are out here, between 230 and 860. Those are kind of moderate. They're between the two toxicity thresholds. And again, we're looking mostly at the west here. And anything in yellow, orange, and red is a concentration higher than what is than what there should be according to state water quality standards. And just in case before anyone asks, the size of the dots on that map are related to the size of the watershed. So for example, this red point at the top is draining this branch, which is a larger watershed area. The smaller yellow dot is just draining this little tributary here. All right, so I want to remind you that these are grab samples, and what a grab sample does is you take a sample at one point in time. And so some of these are the maximum concentration of just 5 values, 5 measurements that were taken. Others are the maximum measurement for over 100 samples. And so I always like to remind people that we have to take this data with a grain of salt. So have to have a little bad joke in there for you. Sure you're awake. Right. So of those 60 some sites that were monitored by volunteers, I took 15 of those sites and put data loggers in the streams. And so those data loggers were reading conductivity during the winters of 2017 to 2018 and 2018 to 2019. So we got 2 winters worth of data, and they were recording a measurement every 15 minutes. And the reason that I was measuring conductivity is that conductivity has a direct linear relationship with chloride. And so the result, and so I'm able to do just some simple math to make a conversion. And so the results in chloride measurements are shown here. So these 2 horizontal lines near the bottom, those are our water quality standards of 860 and 230 milligrams per liter. This is called a box plot, and in case you're not familiar with this, I'll go ahead and kind of walk you through it. These bars, this value down here is the minimum, and the value at the top here is the maximum concentration that was measured. The dark black bar across the middle is the median concentration, and so that means that half of the data collected were higher than that bar, and half of the data that were collected were lower than that bar. And then this blue box in the middle, or I guess towards the lower part, but the blue box is what's called the interquartile range. So that represents the middle half of the data. So like the highest quarter of the samples are above that on that dashed line, and the lowest quarter are down there. So the blue box really represents like half of the time, kind of in the middle, it's in this. So if we're cutting off all of the extremes, basically. All right, so one thing that hopefully you're noticing from this is that we've got these 3 samples, or these 3 streams, where we have maximum concentrations that are about 7,500. So that's about 1/3 of the way to what you find in the ocean. Because if you remember, the ocean, seawater is 20,000 milligrams per liter. And then we have here the River des Peres. And hopefully many of you have heard of the River des Peres. When I'm talking about the River des Peres, I'm not talking about that big open channel down that's the boundary between St. Louis City and county. I'm not talking about that part of River des Peres. I'm talking about River des Peres. Actually, I'm going to go back one slide. I'm talking about River des Peres up here, where it's still actually just a normal looking stream. And in that stream, we had concentrations of over 26,000. And so that's higher than what we find in the ocean. So that's pretty heavy duty salt that time. And we only have 3 of these 15 sites, and all of these are out in the western part of the county. Only 3 of these sites had chloride concentrations that stayed below that acute toxicity threshold. So clearly we have a problem with high chloride concentrations in many of the streams in St. Louis County. Okay, before I move on, I guess this is a kind of a good time to ask if anybody has questions about what I've talked about so far.
So I do, I take it for like river to pear. That's an obvious visual one that people see, and you're right. It's the man-made channel that most people are familiar with. But um, I looked at that area. Any particular reason why that seems to have a lot more salt runoff than? Because we all,
Right.
pretty much every place I know uses some semblance of salt. That even though they're kind of switching over to brine and other things.
Yeah, definitely. If you look at this, you notice that really this blue box isn't really a whole lot higher, and in some cases it's lower than some of the other sites. So it's really just on that extreme end up there that we had those really high concentrations. And I don't have those images in this presentation, but if anybody wants to, I can probably find another presentation from a while back that would have this. But I was actually able to trace that to a couple of specific events and the causes for that. At first I thought, during the winter of 2017 to 2018, that was the winter where it got really, really cold, but then but it was dry, but because it was so cold, we had a lot of water main breaks. I think there were like 2,000 water main breaks in that in that January. And so I thought, well, maybe there was a water main break, and so there was water getting on the road, and maybe they dumped a lot of salt and it just kept washing it in the creek. So I got in touch with the Missouri American Water. They said no, there wasn't any water main breaks around during the right time for that, and in that anywhere near that location. So that wasn't it. And so it's kind of a last ditch effort. I looked at Google Earth and was able to they have that like look back in time at different things, and I was able to see that like a week before the really high salt concentrations, there was an uncovered salt pile about half a mile upstream. And so that uncovered salt pile, it just rained just enough and started washing it in. It didn't rain heavily enough to dilute it, but it rained heavily enough to bring that in. And so, yeah, an uncovered salt pile can do that much damage to a site.
Thank you.
Yeah. All right, well, I will go ahead and move forward with this. All right, so salt accumulation in streams is a problem that we need to solve using via resource use and stormwater management. A lot of the times when we do stormwater management, we're talking about things like rain gardens and stormwater detention basins, like you see in the pictures. And the purpose of those sorts of methods are to allow stormwater to filter through the soil and then into groundwater or through a soil-like medium. And so it can either flow then into the groundwater or into a stormwater system, depending on how they've designed the stormwater management detention basin. So this works really well for things like nutrients and sediments because those are filtered out in that process. But the salt remains dissolved and passes through these filters. And so really the only effective way, at least cost-effective way, to keep the salt out of our water is to use less salt. And so I wanted to study a method that some cities have been using in order to cut their salt use, and that's the use of salt brine. So what is brine? Brine is salt water. And so the practice of brining involves taking the same solid rock salt, the same sodium chloride, dissolving it in water to make a 23% solution, and then spraying it on the road before a storm starts. So you can kind of see this in these pictures. We've got this is just a typical salt truck, and it's dropping the salt and bouncing all over the place. And then you've got the anti-ice liquid, which is just brine. They're applying salt, and so they spray it. And so if you haven't seen a truck putting the salt down, you may have seen the results, because before a winter storm, you'll see those white stripes on the road. And St. Louis County does this in some places, as well as, again, some of the municipalities. So you might have seen this around town. So there's several suggested economic and environmental benefits of brining. One is that it can be done up to 2 days before a forecasted storm. And so this allows work crews to go out during regular business hours, so they don't have to be out there as much for overtime. So it cuts down on those costs. And then according to various studies that were done on highways, you do get the same road clearing effect using half or less the amount of salt. And so that'll reduce some of those negative consequences to wildlife and plants. Now those studies have been done on highways, and there's been other studies that were done in parking lots, but no one has really looked at this in a real life situation in residential streets. And so and we have a lot more residential streets, a lot more miles of those sorts of streets than we do of highways. And so this is a really important kind of gap in there that I'm going to be exploring here in a minute. Now there is a potential drawback to the use of brine, and especially in areas like St. Louis, where it's often difficult to predict the form that a winter storm is going to take. A lot of time a storm will start as rain, and then it could transition into snow or ice. Under these circumstances, if brine has already been put on the road, then the rain will wash it from the pavement, and then road crews will still have to come back and spread rock salt as well, which would both increase the labor and the amount of salt used. So I wanted to basically test whether or not the use of salt on residential roads was effective. As I mentioned, several prior studies were done on highways and parking lots, but I wanted to look at real world applications of brine for storms in residential areas, and the use of this as a best management practice in multiple cities, because a lot of studies like this are not replicated. It's this highway that gets the road salt, and this highway that gets the brine. They don't really have replication in there, which makes it a lot harder to draw conclusions if you don't have replication. So for this project, I studied residential areas in 3 pairs of cities. Each of the pairs was selected to include one city that has a brining system, and those are the ones in dark blue, and one city that does not have a brining system, and so they're just using the solid rock salt. Pairs were set up as neighboring cities to help control as much as possible for the variability of storms as they cross the region, because as you know, if you've ever seen a snowfall map after a storm, you'll have an area in the north of town that has 8 inches of snow, and an area on the south side of town that just has 1 inch of snow, and everything in between. The cities were also paired in order to kind of account for socioeconomic factors like city revenue, per capita income, and the density of development. Those can impact salt use within a city due to the city budget, and possibly resident expectations for road conditions. And then sites were selected within these cities to exclude any areas that have commercial or industrial development where private application on parking lots might skew results. So these are just residential streets that I'm looking at. All right, and this is a kind of odd graph. I mean, it looks kind of simple, but then you have this PC1 and PC2. Don't worry so much about that. It's called a principal components analysis. Basically, the idea is this is a way to look at a large number of variables with just kind of compiling them into 2 axes. And so to confirm kind of that socioeconomic similarity in neighboring paired cities that I mentioned, I used 13 economic, demographic, and land use measurements. And so I looked at my 6 study cities as well as 3 other cities kind of comparable size elsewhere in the county, just to have kind of an outgroup to make sure I'm not biasing my data here. So the first 2 PC axes accounted for 77% of the variability. So it's a pretty good measure. So the first axis here is strongly correlated with economic prosperity. So the communities that are more economically prosperous are over here on the right, less economically prosperous on the left. And that's looking at measures like unemployment rate, income, and percent of people in the community that own their home. And then this other axis, the PC2 axis, is measures of population density and green space, and the amount of paved surfaces. So places that are higher up here have more green space, places closer to the bottom have less green space and more paved surfaces, basically. And as you can see, these paired cities are more similar to each other in these measurements than they are to other cities in the study and other non-study cities. So this is a pretty good way to see that basically the cities that I'm looking at, it's reasonable to put them in pairs. All right, so what I did is during the winters of 2016 to 2017, and then again the following winter, I put data loggers, and you can kind of see one of them here, put these data loggers into the stormwater system to record, again, conductivity, and then I had a second one in that was recording pressure readings, and this was done at 5-minute intervals. And I did this in 4 stormwater pipes in each of those 6 cities, so a total of 24 stormwater pipes. As with the stream data, those conductivity readings were used to estimate the chloride concentration. And then pressure was used to estimate water depth. Once I knew how deep the water was, I was able to use some engineering equations to use the water depth, the size of the pipe, and then the slope of the pipe in order to estimate the flow volume. And then by multiplying the flow volume and the chloride concentrations, I was able to come up with the chloride load at each 5-minute time point, and then the chloride yield, meaning the total amount, for each of 9 storms that occurred over those 2 winters. I also identified the drainage area from each pipe. So for example, here's the outlet pipe in this location. I had to use the drainage, I had the drainage coverage that I got from MSD. And then also up here, here's where the outlet and then where the sampler was, and that drains this area. I had to use that because MSD doesn't always build their system to match the topography. So they can build under a hill. So you might have, where a watershed is defined by the land surface, this had to be defined by the land surface and where the pipes go. So created these pipe sheds, for lack of a better term, and was able to then identify how much road area was in each of these pipe sheds. So this area here and this area here all contribute to this location. And so when I'm showing data here in a couple of minutes, what you'll be seeing is that the chloride yields are shown as grams of chloride per square meter of road. And that's done on a per storm basis. So basically how much salt was taken from the road surface and made it through that pipe during that storm. All right, so I'll be showing some data here in a second. This is what it's going to kind of look like. I want to walk you through this. They're not very typical of how people present data. So I want to make sure that these make sense. On both axes, it's going to be the yield of salt conveyed during one storm event for one of the 2 cities in each pair. So on the x-axis, this is for the city that has brining, that has that technology available. It doesn't mean they use it. Maybe it's not right for a certain storm, but they have the technology available. That's the city down here. The other city is the city that does not have brine available. So every point you see on the figure is going to be a pair of cities for one storm event, one of these pairs for one of the 9 storm events. So any point that falls above this is the 1-to-1 line where they apply the same amount. Any point above the 1-to-1 line like this represents a pair for which, for that storm, the city that has rock salt used more salt than the city that used brine. Any point that falls on the 1-to-1 line means that during that storm, the pair of cities used the same amount of salt. And any point below the line represents a pair in which the brining city ended up using more salt than the city that relies on rock salt alone. So this is what we'll see in this red zone. That's if a city, maybe they applied the brine and then it rained and then they had to apply more salt when the rain turned to snow, something like that. All right, so as you can see, most of the points in this figure are above that 1-to-1 line. There's a significant linear relationship between the paired cities and their salt use. And then also this relationship is significantly different than the 1-to-1 line. So this is our data set, and this is the 1-to-1 line. And that represents a 45% reduction in salt use in cities that use brine. Now, one thing I want to point out is we do have, there's a point here right on the line. This one's a little higher. The line goes directly here to this location. I ran the same tests without this point here at the top, just to make sure that that wasn't like an outlier that was driving the relationship. I got almost the same result. It was, within 5% of this, I forget if it was a higher or lower reduction, but it was still somewhere in the 40s for the reduction if we pull this point out. All right. How does this look if we break it down by city and by storm? So this is the data. It doesn't get much more raw than this. And I just kind of want to point out a few differences among the cities. But first, I'll kind of describe what I'm showing here. These numbers in gray represent the mean yield across the 4 pipes within the city for the storm. So this is an average of 4 numbers. This is an average of a different 4 numbers. It's those 4 locations in that city. And then this number here at the end, this total mean yield, is the sum of the numbers across all 4 storms. Across all 9 storms. Now, for each of these pairs, the one on top is the one that had just the rock salt, and the one that had brining is on the bottom with the darker gray. And the difference is just simple subtraction from this to see what the difference is. So any number that's positive is an instance where the brining city had less salt in their stormwater. So Baldwin, with their brining system, used 21.2 grams per square meter of roadway less than Manchester for this storm. Now, the first thing that I want to point out is that the 2 pairs of more affluent cities, Manchester and Baldwin and Rock Hill and Webster Groves, in those, they use much more salt than Jennings and Ferguson. Even if you add up what Jennings and Ferguson used, that's still less than the lowest number in any other city. There's several possible reasons for this. It could be related to some of those socioeconomic factors that I mentioned earlier, but it could also be associated with the microclimate of that area. The intensity of winter storms in that part of St. Louis County tended to be decreased. And I don't know, that may be due to the proximity of these cities of the Missouri and Mississippi rivers. So they might serve as a little bit of like a thermal buffer to help keep that area just warm enough that the storms don't tend to convert to snow and ice as readily. Next, if we look at the Manchester-Baldwin pair, there's several storms here that have an asterisk next to them. Those are storms for which the city reported using brine. And you can see that in all of those instances, Baldwin had a lower salt yield than Manchester. Unfortunately, salt usage data were not readily available from the other cities as far as like what dates they put it down. All right, and then let's see. Oh, and then looking at the third pair of cities down here, Webster Groves had a lower salt yield for all storms. So the difference is always positive there. And they ended up using quite a bit less salt than their neighbor Rock Hill. And then finally, just looking at this third storm on January 13th of 2017, this storm represented the greatest salt yield for 5 of the 6 cities. And it was definitely the biggest winter storm over this 9-storm period. And in every instance, the brining city ended up using less salt. All right, so the conclusions from this is that brining does lead to approximately a 45% reduction in chloride. So that's good news if we want to try to use reduce our amount of salt use. Brining is a management practice that works even in St. Louis, where we a lot of times have difficulty kind of predicting how the storm is going to fall out. But salt use definitely varied by city pairs and by storm. Now, this isn't a surprise because each city is run independently. Weather patterns can change over a short distance, and the severity and duration of every storm is different. And so public works departments are doing they're doing a good job at responding to each storm individually. Okay, so all of these numbers are great, but what does this kind of salt reduction look like in the real world? Well, to find out, we're going to do a little visualization. Just imagine a residential street about 7 meters wide. And what we're going to do is we're going to think of just a 1 meter stretch of that road. And then what we're going to do is we're going to take one of these containers of salt. I don't know about you, I have one of these in my kitchen. You know, you get them at the grocery store so you can refill your salt shaker. Instead of filling your salt shaker, you're going to take that salt and you're going to sprinkle it over that short stretch of road in the picture. And then you're going to do that 4 more times. That is the amount of salt that the cities that use brine did not put on their roads, but their neighboring cities did over those 9 storms over the course of 2 years. So this represents a savings of about 1.5 tons of salt per lane mile of road per year. So a lane mile is basically 1 lane of a road that's 1 mile long. So for most roads, you know, most residential streets are going to be 2 lane miles, or 1 mile of road is 2 lane miles because there's 2 lanes. According to transportation data, in the state of Missouri, there are about 48,000 lane miles of urban roads that are classified as minor arterial, collector, and local streets. And so these are the types of roads that cities will put the salt on for the most part. So by using brining, cities could cut approximately 71,000 tons of salt per year just in cities in Missouri. So if this is saving $50 per ton in purchasing and $600 in infrastructure damage, that's a total of $46 million per year just on the urban streets of Missouri. That's a pretty impressive savings to me. Now most things that save money and or protect infrastructure are also bad for the environment. So let's look at this from an environmental perspective. All right, so what we're going to do is get one of these kiddie pools that you'd find at your neighborhood big box store and fill it with 8 inches of water. So that's about 100 gallons of water. Now you do that same thing, you fill up 7 more of those. So you've got a total of 8, and you're going to sprinkle your container of salt in those. At a concentration of 230 milligrams per liter, all of this water is now considered chronically toxic to aquatic life. But when we did that before, for this lane mile of road, or not lane mile, for this 1 meter wide stretch of road, we used 5 containers of salt, not just 1. And so we need 40 kiddie pools for this 1 stretch of road. So that's about 4,000 gallons of water that is protected by using brine in this 1 short stretch of residential streets from 9 storms over 2 winters. Let's take that a little further. So this amount of water per lane mile per year is the equivalent of filling about 2.5 Olympic swimming pools, or almost 10 Washington monuments, filling them completely up with water that is toxic to aquatic life. So if we again multiply this by the lane miles in urban parts of Missouri, we get about 77 billion gallons of water per year. As you can tell, I have a lot bigger difficulty putting this in forms that I can visualize. But just to kind of give an idea, this would be the equivalent of a cube of water covering the area of 25 football fields with contaminated water. You know, football season starting, we've seen a football field maybe recently. 25 football fields covered to a depth of 1 mile every year from the urban areas of Missouri. So yeah. If anybody has other ideas on how to visualize that amount of water, feel free to let me know. I just, you know, I can't, I mean, I don't know how many 1 gallon aquarium or 10 gallon home aquariums that would be, but it's a lot. I guess if it's 77 billion gallons, it'd be, you know, 770 million, no, 7.7 billion aquaria. which I can't visualize that either. So if you have a way to visualize it, let me know, because I can't do any better than this. So I hope you found this informative. It's not a good science talk unless you acknowledge the people who helped you do it, and it's definitely an important part of the talk. I'll be glad to take your questions, but I need to thank, I mentioned the EPA Urban Waters program, that their grant funded this project. The PEO fellowship, they gave me money to help me finish out my PhD, MSD, and the other participating municipalities for the information that they were able to share with me. The people on my advisors for my PhD, and then those who helped me with my field work. But more so than that is I really want to thank the Missouri Stream Team volunteers, because that group inspired me to not just do this work, but to get a PhD. I'd thought about getting a PhD before, but I was like, I can't think of anything I want to spend 5 years of my life looking at that in depth. But the Stream Team found something for me. So with that, I will gladly take any questions.
Danielle, is there any other option besides the brining that you could think
There
of?
are other options. Basically, every option has its negative points. So for example, there are places where people are starting to use beet juice or pickle juice or some kind of basically a liquid sugar. And so putting the sugary type product on the road also will decrease snow and ice buildup. But rather than being toxic to aquatic life, adding sugar to water increases the bacterial growth. And so the bacteria will then suck oxygen out of the water. And then instead of being toxic conditions, then we just suffocate them. So, and so it's possible that some combination of different things, you use less salt and less sugar. So you have a little bit of both problems. That would be, in my opinion, the best solution is just don't use salt. I mean, somehow we managed to survive for decades in cars without having, without doing this. Maybe just get off the roads a little more when it's snowing. In my personal perfect world, residential streets, you just drive really slow, and maybe use salt when there's, a specific turn that's dangerous or what have you. There's going to be exceptions, but maybe use salt on one lane of the big multi-lane arterial streets and don't use it on residential streets. You just have to drive slow for the first or last 3 blocks of your trip, That's my personal preference, of course.
What about sand?
Just do better as much as possible.
So I'm curious if you're watching anything concerning the I don't want to say a pandemic didn't hit the right time period for you, but it kind of didn't. Right? There's no big impact, and depending upon what happens in the next 6 months, you may not get any data from it. But it'd be really interesting to see. I mean, I know there are studies now that said pollution is down dramatically because there aren't as many cars driving. And I'm kind of curious if the same will be impactful if this thing does extend into the new year at all. Is that something you're watching at all, or would be able to watch?
I'm not. There's a possibility, but there's enough people who are still on the roads that if the road isn't cleared adequately, then one, there will be an increase in accidents, and because people are like, oh, well, there's not as many cars, so I can drive faster, even though there's snow. When it comes to driving, a lot of people don't seem to exercise common sense. So I think they will still use the same amount of salt because there will still be cars on the road, basically is what it comes down to.
What about using cinders and sand like they do in New Hampshire?
Right, so those also have effects. Cinders, I have no idea what's necessarily in any given, in the cinders in any given area, but from what I understand, that being a burnt material, there's a chance that it has all kinds of heavy metals in it, depending on where they get them from. And then sand, there are places where they put down sand and then they have to sweep it up and recover it. And any amount they don't recover, they might be like not fined for it. There's a fee that's paid for that. But the difficulty with sand, if it isn't recovered, is that it can, when that washes into a creek, it will fill in the stream bottom. And if you, for example, if you have a stream that normally has a gravelly bottom, and then you have all that sand coming in, you can suffocate the habitat that the different invertebrates and fish need. So for a while, I think that was a big problem for some of the fish breeding habitats.
I think in New Hampshire, they reuse the recovered sand.
Right, right. So yeah, if they're recovering it, that might be a pretty good option. But if it's not recovered, or whatever portion is not recovered, whether it's all of it or 10%, it's going into the streams if it's not being recovered.
Well, actually there they have really sandy soil, so maybe it's not as noticeable.
It's possible. I don't know. Yeah.
Danelle, have you
Danielle, I see.
your findings to other municipalities around St. Louis County? I mean, the obvious thing is the reduced cost for staff of storage of salt. Just, you know, there just seems to be all kinds of good benefits all the way around.
There are, and there's a lot of cities that are interested. I've spoken to meetings of the, like the St. Louis chapter of the Society of Civil Engineers. I've spoken to 2 different stormwater management groups in Illinois, you know, just across the river. MSD is fully aware of this, and I've given presentations to Deer Creek Watershed Alliance. I think the word is out about this, and actually I also spoke just a couple months ago to the Water Protection Forum for the state of Missouri. So yeah, people are hearing about it that need to hear about it. I didn't, you know, this is not something that I just wanted to tell the scientists, because that's not doing anybody any good, because it needs to go to the people making policies and purchasing equipment. So yeah, I made sure to do that.
Danielle, I see some members that are typing in questions in the chat box.
Oh,
I see Cindy Leader has asked, do you have a homemade brine recipe for our sidewalks and driveways?
I don't, but I think that if you have, I know that for saltwater fish tanks, I forget what the name of the little piece of equipment is, but there's like something that you put in your tank, like a little instrument to tell you how salty it is, because different, you know, you need to have the right amount of salt for the fish tank. And so if you have one of those, if you can get it to something around 23% or even 20% would be enough. Then yeah, I've had a colleague from SLU who got just a spray bottle and was spraying that on her own sidewalk and walkway, you know, to see if that would work. And it seemed like it worked pretty well for her. I'll have to look for a recipe and I can pass it on to you, Bob.
You could do it with a balance, just weigh it.
Yeah. I mean, it's 20% or 23% solution. So yeah, if you have a balance, that would work too. I don't think I have one of those at home.
Kitchen scale would work.
Yeah. Yep.
Cindy also asks, has anyone studied car accident statistics with brine versus salt?
I'm fairly certain that someone has, but short of statistics, there have been on the highways, and on the parking lots as well, and the studies that they had done. It may not have been crash statistics, but they did look at how quickly the pavement cleared. So it went from being whatever percentage covered in an untreated area, and then they treat, you know, areas that were treated with brine and areas that were treated with rock salt. And the brine was either comparable or better, because what the brine does, having that layered down before the storm, it prevents the ice or snow from adhering to the pavement in the first place. And so it's able to clear a lot faster and not have that initial buildup that you might get otherwise. Because otherwise they don't put salt down usually until you've got 1/4 inch of snow, or it's been, you know, they have to.
They put it on top of the snow.
Time it takes to get to your street before they can put it down. So.
And that seems to be the effective part of it too, right? When rock salt mixes with the water and then becomes brine and spreads out, that's when it's most effective at getting rid of the ice. So,
Right.
so do you see
That's-
a big trend towards that? I mean, what you're showing here seems obvious to the most casual observer that they should be doing this. It's cost effective. It's better. It's more effective. It's better for the environment and everything.
Right.
Cost above all would be a thing that you would think would drive every municipality. But is it just because the retrofit issues that they have to be able to get trucks that spread brine as opposed to salt?
Right. Well, it's partly retrofit, but to some extent, it's not even retrofit. It's a whole different set of equipment, because they will still have to spread. You know, let's say that you get a 4-inch snowstorm. The brine will take care of the first inch or so, but after that, they'll probably have to reapply, at least in some areas. And so they still have to have those salt trucks. But in addition, they have to have a brine truck or two, and they have to have the mixing equipment to prepare the brine. And so there is an investment up front, but that can be done in several different ways. Just within this study, Jennings was one of my brining cities. I believe, and I can look up the details if anybody wants, but I think they got their equipment for about $20,000. They got it secondhand. Or parts of it they got secondhand, other parts they built in-house. So that was kind of a low-end one. Webster Groves, I think they spent like $110,000 on their equipment, and then Baldwin spent like $180,000. So you could go anywhere from a build-it-yourself sort of setup to a much more fancy setup. So you know, there's a lot of variability in the initial cost. And then kind of as a non-municipal example, at Washington University, when they heard about this, they went ahead and the people out of the Tyson Research Station, they put together their own equipment. I mean, they already had water tanks. They already had, like, I think they spent like $200 on PVC and some fasteners and things, and they built their own brining system. And that's what they've been using. You know, they've got a mile or so long road. So they just do 2 passes on that. And it took care of all of, you know, that's all they had to use one year. They didn't even have to put down salt. So they cut their use by 75 or 80%.
They also got a school of engineering that probably helped design that little sucker too.
No, I think it was just the people at Tyson that, you know,
okay.
they have their own maintenance crew out there. I think it's like, you know, 2 guys that build stuff, maintain stuff and whatever. Yeah, they took care of that.
Very
I think
cool.
there was no engineering involved. So it doesn't have to be a complicated system.
No.
It's just to spread liquid on a road.
Does spooting the brining first help with the snow plowing effect? So like if the snow's really deep and you've already brined, do the plows, are they able to move it off better?
I'm not sure. It certainly shouldn't, it wouldn't hurt. I don't know if it helps, but I mean, with the brine being at the bottom, maybe it kind of keeps an open, more loose layer. Like I said, it doesn't adhere. So if the snow falls quickly enough, then yeah, that could probably help with that as well.
Danielle, here's another question that was written in. Linda Cook asks, do you have a recommendation for the best product we can buy for our driveways, sidewalks, etc., that would be the least invasive to our environment?
Right. So what I suggest at home, especially on stairs and sidewalks, is just using sand. And if it's a high traffic area or you're especially concerned about getting it to melt, maybe mix a little bit of salt in with the sand. And I say that because if, you know, the amount that you would in theory be using, when that washes off, it's probably going to end up washing into your lawn or landscaped areas where it shouldn't do any damage there. I mean, I guess maybe over the course of 100 years, you might put enough salt or put enough sand down that you might need to do something about it. But generally speaking, you're not using so much sand. So, and again, that kind of depends a little bit on situations, you know, on a north facing stairway, and, you know, that, you know, maybe steep, you might just have to use salt for safety reasons if you have to be going in and out through that pathway, because, you know, it's not worth it to break a limb at this point when you're trying to get out, especially, you know, again, in St. Louis where we have a lot of ice. If it's icy situation, you know, safety first, really. But otherwise, yeah, so brining, sand. Some people use bird seed. I would be cautious about that because some bird seeds are very, some of the bird seed has very round seeds, and you have a round seed on top of ice. I can think that could just be a catastrophe. So other people have told me that they use bird seed, but like I said, be very cautious with what type of seed you're putting down and possibly making your situation worse. Yeah, that's unfortunately about the best advice I can give. As far as the stuff you would buy at Lowe's or Home Depot, I don't know enough about any of those specifically. What I do at home is there's been times when there was like a pile of salt left over in the road, or where I was pulling large grains of salt out of my grass from when the truck went by. I collected those. I have a collection of that in my kitchen that I just crush it up and sprinkle it and figure I've done better than going out to buy some. So,
That's good.
reduce, reuse, recycle, right?
I use a snow shovel in the sun. My driveway faces south. As soon as I get it cleared off, it doesn't have to be very sunny, but as soon as I get the snow off it, it'll be fine. I won't have to put any salt or sand on my driveway.
Yeah. Yeah, that's definitely
It is blacktop too, so it is asphalt. So,
right.
but it doesn't take much sun or it doesn't even have to be sunny as long as it's daytime.
Right. Definitely. Yep.
Bob, you're on mute. I can read that one if you like, but you're on mute. Go ahead. Oh, anyway, Bob, the next one is, are there any Audubon statistics on areas that use salt versus brine, like more birds in brine areas? That was from Cindy Litter.
Not, if there is, I don't know about it. I haven't really thought about salt versus brine in the context of birds. I mean, most of the water birds are utilizing larger bodies of water, at least for a large portion of the time. And over winter, salt concentrations in the summer are increasing, but they're not like through the roof like what I've showed earlier. And I would think that most of the use of small streams by water birds is going to be in the summertime. And I could be off on that, but I know that in my experience, I see a lot more birds, in and around the water in the summer and, well, spring, summer, fall, not in the winter when we have a lot of salt use. Because most of the increases in salt in our creeks and streams it's kind of like the flow in our areas. It's very flashy. So it will go up very high very quickly and it will drop right back down. So yeah, I'm unaware of anything about birds and salt brine though.
Danelle, I have a hunch that you might know the answer to this question. It's somewhat related to the first, to that one. Are there any statistics on the effect of salt and the aquatic critters in the stream?
There is information on that. And you're helping me write a paper on some of it. So yeah, I mean, so those aquatic toxicity limits have been generated based on data collected by scientists. Most of the limits were originally written based on laboratory tests where they take 200 animals of 200 each of types of animals, like 10 different species in 10 different groups, and put them in containers that have different amounts of salt and find out how many survive. It's not a way that we like to do it, but it's done generally using laboratory reared animals. So it's not like we're taking a sensitive population and taking half of the animals away from it. So that's how those were originally set. More recently, it's kind of using nature as our laboratory. Those data that I showed earlier, let's see if I can go back to it. Let's see if it shows up. Oh, no, I got to go back on this one. Excuse the, there we go. Okay, so, so this is like I mentioned earlier, this is the stream team data of how much salt we have. And the stream team also collects invertebrate samples. And so the project that I'm working on with Bob and Claire, who I believe is in your group, and then another citizen scientist, we're going through and comparing the chloride data that was collected by the volunteers with invertebrate data that was collected by volunteers. So we're writing up a paper on that. But then also, oops, wrong way. This data with all of these sites where I have data at 15-minute intervals, I collected invertebrates from all of these sites, and I'm going through the process of trying to identify all of them at this point and find out, you know, how are the communities, the invertebrate communities, different from one location to another based on the amount of salt that they're exposed to. And the short answer is more salt is bad. But there's also the possibility in any given location that there might be some kind of confounding effects from other problems. Like, you know, is there also a habitat problem, or is there also a high nutrient problem or a low dissolved oxygen problem? You know, trying to eliminate other possible causes for that community to be in a poor condition.
Very good.
Other questions for Danielle? Anybody?
Thank you.
Hey, Danielle, thank you so much for taking the
Oh,
time
absolutely.
for rescheduling
Oh.
and all that, and gave you
Yep,
time to get your doctorate, I think, didn't we? Didn't
Well,
you?
yeah, that's about, we were scheduling it around that time.
Ah, that's true. So, yeah, no, thanks so much. And I did notice a number of names there that we recognized. We saw Bob's name up there. We saw the Schweitzer's name there. I think I saw a couple other members that I saw up there too.
Oh, there were a lot. Corey Westcott was there.
I saw Corey.
Claire was there. Claire Byron.
Yep.
Very good. Very tight.
The big group.
Yeah, it's a great group of volunteers, and I'm honored to have been one of them, and to sort of still be one of them, and to work with them and making a difference. That's, for me, that's what it's all about. It's like, there's no point in doing the work if it's not going to result in some kind of improvement, some kind of change.
Absolutely. Well, very
Let's
good.
let's call for a big round of applause. If everybody unmutes themselves, we'll do a hand clap in 3 seconds. 1, 2, 3.
Thank you.
Very good.
Very good.
All right, Daniel, you're very
I'm
welcome.
going to sign off because I think I'm going to sign off because I've got a kid that needs some homework help. So,
Understand. Thank you so much again.
all
See you
right.
soon.
Good to see you.
Here.
Bye.